recording it. Okay. So does everyone have their table or a copy of one? Who does not have one yet? Okay, so we will wait until you guys get one, and then we will start by first learning how to use this table, okay? And then we'll get into everything else. But we first have to know how to use this table, otherwise we will run into problems. Or actually, while those tables are being passed out, let me do problem 845 from the book. I know there was no answer posted online. So you can take notes on this and then compare your answers with what you did in the homework. This is chapter 8, problem 45. This homework was assigned, but there was no video for it, okay? Okay, so I'm assuming everybody did the homework, everybody read this problem, and maybe you struggled through it, maybe you got the answer, maybe you didn't, okay? This is the idea. They've done an experiment. They had a whole bunch of people, you know, over 2,500 something, okay? 1,287 were given the drug Vioxx. 1,299 were given a placebo. All right? And they monitored all of these people, and some of them had heart attacks. Okay? So for the Vioxx users, there were 1,287 people. 45 had heart attacks, giving us an overall percentage of heart attacks to be 45 divided by 1287. P hat, I'm going to call this P hat 1 is equal to 0.03 496 or 497, so I'm going to just round off to 0.0350. Okay. Placebo. There were 1,299 people. 25 had heart attacks. Is that right? Let me just double check. Yeah, 25 had heart attacks. Ask you guys to just be quiet. And so this gives an overall percentage of people who had heart attacks to be 0.0192. Okay? So the idea behind this hypothesis test is that if we were to take another sample, basically 1,300 people, give them Vioxx, another 1,300 people, give them the placebo, and we monitored them, some of them would have heart attacks. Would we have 25 people have heart attacks and 45 people have heart attacks if we did this experiment again? Probably not. Probably not, okay? Those numbers will be different. So we know that these numbers that we observed, 25 and 45, is a result, partially, of random chance that the people we selected, different rates of them have heart attacks. Okay? But the question is, I saw 25 placebo users have heart attacks and 45 Vioxx users have heart attacks. Is the difference between that, is that significant, or could it be a result of random chance alone? So when we write our hypotheses, the hypothesis is that P1 is equal to P2, meaning the proportion of Vioxx users who have heart attacks is the same proportion of placebo users who have heart attacks. Okay? And if this were true, then that means the only reason why I observed a difference in my data is because of random chance. Okay? So again, the null hypothesis says that the proportions are the same. We observe a difference in our data, and that's a result of random chance alone. The alternative says, no, there's actually a difference. And the way the question is written is, do Vioxx users have a higher rate of heart attack than the placebo users? Heart attack. So we have to get our z-score, our test statistic. It's going to be p1 hat minus p2 hat, technically minus 0 divided by our standard error. The standard error is given by this formula. P hat times 1 minus p hat over 1 over n1 plus 1 over n2. And p hat is given by total success over total observed. So I have 45 plus 25 over 1287 plus 1299. 70 over 6. Keep this place. 0.0271. This is p hat. So I plug that in up here. Oh, okay. 2.48. What's that? Oh, bless you. Yes. Okay, so I'm right here. I go to 2.48, and I want the area over here. So here I'm looking in my z table, and I look for the area to the right of 2.48. And I get 0.0066. Okay, so my p-value is 0.0066. The p-value is the probability of observing our data from random chance alone, or observing our data if we assume the null hypothesis were true. Okay? So if Vioxx users and placebo users truly have the same rate of heart attacks, is it possible that 45 people who use Vioxx get heart attacks from random chance, and that 25 people who use the placebo have heart attacks by random chance? Is that possible? Yes, it's possible. But how likely is that to happen?
Unlikely.
Unlikely. The probability of that happening is less than 1%, 0.0066, okay? So about 0.7%. So it's unlikely to happen. Is it possible? It is possible, but it's very unlikely. So rather than just saying we happen to have a freakishly unusual sample, what we conclude is that this is actually evidence that Vioxx increases the risk of a heart attack. So my p-value is small. Okay, my p-value is less than 5%, which we would assume is alpha. Okay, so generally our significance level is 5%. Our p-value is less than 5%. So we reject the null hypothesis. It is highly unlikely that we observed our data from random chance alone. Instead, we conclude that our data provides evidence that our data provides evidence that Vioxx increases the risk of heart attack. Okay, there you go. That's problem 845. You laughed.
No, you're saying, so that's all? I laughed.
Yes. No problem. Oh no. I don't have any eraser. sure. All right, let me go look for you.
Why do we have like we have whiteboards like this and chalkboards
All right. Does everyone have a table now, or access to a table or something?
How was your birthday?
It was great.
We're with them, like we saw them that day.
What's that? What did I do?
We weren't even open.
All right.
I tried to. Yeah, we tried to, but I wasn't
All right. Let's look at our table. Page A7, T distribution critical values. And it has a picture like this. And it keeps going to the right. Okay. So the T distribution has something called degrees of freedom. And we'll get to this in a little bit. But degrees of freedom is related to your sample size. You have a bigger sample, you have more degrees of freedom. Smaller sample, less degrees of freedom. Okay? For now, we won't worry about it, but it comes into play. So let's say we have a problem where we have 9 degrees of freedom. Okay? So I'm just going to copy the numbers from that row that says 9 degrees of freedom. And the numbers that I have are 1.383, 1.833, 2.262, and 2.82. Yes. That's a 9. Did I write something down wrong?
Oh no, sorry.
Okay. All right, is this okay? I just copied the row that has a 9 from the table and just the first 4 columns. Is that okay? We're in agreement with what we see in the table and what's on the board? Okay, so the T distribution works differently from the Z table, the Z distribution. And basically, we're just going to look at this row that has the T.10, T.05, T.025, T.01. The T distribution looks a lot like the normal distribution. It's centered at 0. Okay? And if I were to shade everything to the right of 0, how much would I have shaded? 50%, 0.5. Okay? These are what these numbers mean. It says if we're looking at the T distribution with 9 degrees of freedom, so here I have degrees of freedom equal to 9, and it says if I draw a vertical line at 1.383, the amount that I would have shaded if I shade everything to the right is 10%. Okay. And that's because 1.383 corresponds to t.1000. So it says if I draw a vertical line at 1.383 and I shade everything to the right, I would have 10%. Okay. The next number says if I go further away from 0 to 1.833 and I shade everything to the right, how much do I have shaded? 5%. Does that make sense?
Yes.
At 1.383, if I shade everything to the right, I have 10%. If I go further away to 1.833, how much do I have shaded? Even less, at 5%. That's what this table means. Okay. One of the most common questions that people ask is why these numbers get bigger going to the right, but the numbers up here get smaller. And the answer is because when you're close to 0, you have a lot. But as you get further and further away from 0, how much do you have left? The amount that you have left to shade to the right becomes smaller and smaller. Is that okay? Alright, so if I were to go further away and draw a vertical line at 2.821, how much do I have shaded in this little?
1%.
Yeah, the amount shaded is 0.01, okay? So it's 10%, 10% everything to the right of 1.383. It's not just 10% from here to here, it's 10% everything to the right is 10%. Everything to the right of here is 5%, everything to the right of here is 1%. Is that okay? Okay. Alright, so that's fine and dandy if our test statistic, our t value, turned out to be exactly one of these values. Okay. What if I get a number like 1.5? What if somebody says, I'm going to draw a line at 1.5? How much will I have shaded to the right of 1.5?
7%.
Okay. Alright, so do we have an answer?
Do you want the percentage?
An approximate value. Okay, so if I drew a line at 1.383, how much do I have to the right? 10%. And if I draw the line at 1.833, how much do I have to the right? 5%. If I go somewhere in between at 1.5, how much will I have shaded to the right?
Between those two.
Yeah, okay. So some of you guys are saying like 7%. That sounds like a reasonable number, but we're not going to go with reasonable numbers. We're just going to say, we're just going to give a range. We're just going to say, I don't know exactly how much we have, but the amount in the tail, whatever it is, the amount in the tail is going to be less than what number, but more than what other number? No, the amount in the tail is going to be less than 10%, but more
Then 5.
than 5%. If I draw t equals 1.5, and I want to make sure that makes sense. So I don't know exactly how much is shaded, but I do know it's less than 10%, but more than 5%. Question?
So what's our value? Like, how do we indicate what t is if t is up there as well? Like, I'm kind of confused with like the columns and like how we're
So these are just
distinguishing
areas,
it?
okay?
Okay.
These are just areas associated with the T distribution.
Okay.
These are the lines where, the values where you're drawing your vertical line and shading everything to the right. The top of the column just tells you, or at least this row tells you
What area?
the area. Okay, is that okay? Alright, so we're just gonna try a few practice questions. Okay, and then before we do the practice questions, let me just ask you one more question, okay? What if I was not going to draw a line at t equals 1.5? What if I were to draw a line at t equals 1.0? How much would I have in my tail? So 1.0 is somewhere like here. How much would I have if I shade everything to the right of 1.0?
The side is smaller than 0, bigger than 10%.
Between 10% and 50%, okay? So the amount in my tail is going to be less than 50%, but more than 10%. Is that okay? Now, oftentimes, for these problems, it's assumed that all tails are going to be less than 50%. So a lot of times you will just see that the tail is more than 10%. Okay? Because we're kind of assuming that the tail is always going to be less than 50%. Okay? But if we draw a line at 1.0, we don't know exactly how much is in the tail, but we do know it's more than 10%. Okay? And also less than 50%. Is there any questions or confusion regarding this? Yes.
I don't really understand how the 1.0 is less than 50%. I see the 10%, but...
So, if I draw a line at 0 and shade everything to the right, I would have 50% shaded to the right. Okay? Now, I'm not shading at 0, I'm starting at 1. So how much will I have to the right?
Okay,
It's going to be less than 50%.
Okay.
But I'm not all the way at 1.383, so I do know it's more than 10%. Okay? I know it's a huge range, but that's just how the t-table works for these in-between values. Okay, so I'm going to put a few drill problems on just using the t-table. Okay, and once we get comfortable with the t-table, we can jump into chapter 9 and have a jolly old time. All right. Okay, so let's say you have degrees of freedom equal to 12 and your test statistic is equal to 2.681. How much is in the tail? Let's say you have 20 degrees of freedom, and your test statistic is 3.7. How much is in the tail? And let's say we have degrees of freedom equal to 5, and your T is 2.7. How much is in the tail? Okay, so you got 3 problems. And for each of them, I want you to figure out your tail area. look in your book, your T-table, or the handout, share with a neighbor. Figure out your tail area. Yes.
For the second one,
I think the second one is like that.
The first one you just find.
Yeah.
That's it's a question. Okay. How are we doing? Okay. First one. What is my tail area?
1%.
0.10.
Okay, 1%. 0.01 is my tail area. Questions on this first problem? No. Okay. So that's good with everyone? Good. Alright. Huh? You don't get it. Okay. Do you have a table?
Yes.
Alright. Do you see the row degrees of freedom 12?
Sorry, what?
Do you see the row that says DF12?
Yeah.
Okay. Do you see a number 2.681 in that row?
Yeah.
Okay. What is at the top of the column that has 2.681?
1010.
Alright. Okay. Next one. Yes. Okay. What is our tail area?
Less than 0%.
0.001. Okay. How did I get that? Yes. Question. That's exactly right. Okay. So if I were to draw this picture for degrees of freedom equal to 20, the biggest number that we have is 3.552. And according to the table, it says if I were to go to 3.552 and shade to the right, I would have exactly 0.001. But I'm not shading at 3.552. I'm going further away to 3.7. So if I shade everything to the right there, how much do I have? Well, I don't know exactly how much, but I do know it's less than 0.001.
So we just write that, like that's less than.
You just write tail is less than 0.001.
So we wouldn't put anything in, like, in between because it's like assumed it's like asymptotic or something, we don't.
Well, I mean, it's going to be in between 0 and 0.001, okay? But it's also assumed that your tail is always going to be more than 0, okay?
For tail, can we just put T?
Don't write
Less than?
T, okay? Because T is your 3.7,
Oh, okay, so
okay?
tail
You don't want to
greater than-
you don't want to confuse your T with your tail. Is that okay? All right, here's another thing to note. All of these numbers, if I were to use T equals to negative 2.681 and ask for the tail area, it would be the same idea except at negative 2.681, the tail area goes to the left, but my answer would also be 0.010. So if you get a negative number, just treat it positive and continue on, okay? But just know that for a negative number, you're looking, the tail means going to the left, okay? Because the table is, the distribution is symmetric. Is that okay?
Yes.
Good, all right. So lastly, we have degrees of freedom equal to 5, and my T is 2.7. How much is in my tail?
1525 on the
Okay, my tail is going to be less than 0.025, but more than 0.010. If you had it, yeah, if you have it written this way, that's exactly the same thing, okay? Both are equally valid. Alright, and we're all good with the less than greater than the alligator mouths. It's eating the, or Pac-Man prefers to eat the bigger number. Yes?
Are you gonna have us just find stuff like this on the quiz?
No. Alright, sorry.
So this is part of the bigger
This is just part of the bigger problem. Okay, just like you have to look up numbers in your Z table to get the areas to get your answer, okay? Just like that, this is in the context of a bigger problem, and this is one step, okay? But if I don't teach you how to use the T-table now, you know, it's, it just confuses people if I'm teaching the middle of the problem and I say, okay, now this is how we learn how to use the T-table, okay? Yeah, Rudy.
So if our, if the T, whatever the number is, if it exceeds what's on our table, we always just write less than or greater than? That's
Yeah,
it?
just write less, if you know, if it's in a situation like this, 3.7, our tail is less than 0.001. And the other situation with my T is 1.0, then I just get my tail is greater than 0.1. Okay? Alright, is this good? Comfortable with using the T-table? More problems?
Please.
Okay, alright, okay, so let me just add another, so I already told you what happens if you get a negative number, okay? There's also a situation where you have a certain degrees of freedom, but you cannot find that degrees of freedom in the table. So let's say you had 75 degrees of freedom, okay? So let's say you have 75 degrees of freedom. What do? Okay. Always round down. Do not use 80 degrees of freedom. I know in your table it says there's 60 degrees of freedom and 80 degrees of freedom, and 75 is closer to 80, okay? However, the rule is you always round down, okay? So always, if you cannot find your degrees of freedom, always round down. Okay, so we would use 60 degrees of freedom, okay? Alright, and then let's say our T was negative 1.72. How much is in my tail? negative 1.72, you have 70 degrees of freedom. 75 degrees of freedom. What do we have? Okay, so figure this out quietly. Okay, so what's our answer? So my tail area is between, or is more than what and less than what?
Between 2.25 and 2.5.
Between 2.5% and 5%, okay? My tail area, and you might have them pointed the other way, and that's fine. You might have 0.05 greater than 0.025, less than whatever, okay?
But isn't that wrong?
What's wrong?
If you did 0.05.
Can you write the other one?
Could you do the drawing?
So this way the
I know what you're saying, just point.
alright, you gotta be comfortable with how it's written both ways, okay?
Just for, specification.
I know, alright.
Could you also draw it?
It's like the pencil.
Sure. For you guys, no problem, alright? Sarcasm, I'm being totally sincere, alright? What do I have? I got 1.671, and here I am at 2.000, and I'm going to oh shoot, negative. Well, this would be if it were positive, so I want to know how much is here. I got 0.025. Beyond here, I've got 0.05. So in here, I've got something in between.
So even if our t is negative, we just treat it the same on the table when we read
Yes. So I have a negative 1.72, but I look it up on the positive side of the table because it's symmetric, okay? So just imagine there's a mirror here. And what do we have? We have the exact same thing, but the negative side. Yes?
On that one you just drew,
What's
that
that?
line, the
Yeah.
third one,
Uh-huh.
would that be the 2.00 or would that be
Yeah,
the one?
this would be negative 2.00.
Oh.
And this would be negative 1.671. And this would be negative 1.72.
Okay. Thank you.
Okay?
Yes.
And tail means to the left now, on the negative side. Okay. We shouldn't spend much more time on this, okay? But if you have trouble, ask your neighbor, all right? Or ask me in class, okay? All right. That's kind of intimidating.
I feel like it's staring right at me.
Huh?
I feel like it's staring right at me.
All right. Let's start with chapter 9 now. So in chapter 8, all right, without even looking at your book or anything like that, in chapter 8, what kind of variables were we dealing with?
P, A, I, P.
Okay, we were dealing with P. All right, let me ask you this question. Were we dealing with numeric variables or categorical variables? Categorical variables. Great. Okay, so chapter 8 was all about categorical variables. Asking things like, what proportion of the Legos were blue? Okay? The color of the Lego is a categorical variable. It's either blue or it wasn't. Okay? Or the candy was red or it wasn't. That's a categorical variable. We had proportions. And in chapter 8, with proportions and categorical variables, you use the Z table. Okay? So keep that in mind. It will be important as you work through the final categorical variables, Z table. Okay? In chapter 9, we are going to deal with numeric variables, and we're going to use the T table. So chapter 9, we will be doing confidence intervals and hypothesis testing. Okay. Or numeric variables. And in chapter 9, we will always be using the T table. Okay, so we're going to have situations where we have one sample and situations where we have two samples. Okay, we're going to start off with one sample. So if we are doing a confidence interval, one sample, and we're doing numeric variable, and it's a confidence interval. If it's a numeric variable, our confidence interval is going to be about mu, the population mean. Okay? Confidence interval . And just a quick check of your understanding. In chapter 8, if we had one sample and we made a confidence interval, the confidence interval was about what letter? It was about P. In chapter 8, we made a confidence interval. You guys took a quiz on this, and the confidence interval was about P. And P is the population proportion. Okay? So chapter 8, confidence interval, or it was chapter 7 and 8, okay? Confidence interval, population proportion, P. Chapter 9, confidence interval is about mu, population mean. Your data, the data used, will have at least these three components. N, what is N?
The number in the sample.
Sample size. We'll also have X bar. What is X bar?
Mean.
The mean of the sample, okay, or sample mean. And it will have S. What is S? Sample standard deviation. Okay, so any problem that asks you to make a confidence interval for a numeric variable will have at least these three pieces of information written somewhere in the problem. Okay? There might be other bits of information in there to distract you. But you are looking for these 3 bits of information once you know that you are dealing with one sample and a numeric variable. Okay? So as you're dealing with problems, don't be distracted by the other thing. Just know I've got one sample, a numeric variable. I have to find n, x bar, and s. Alright, and so the formula for a confidence interval for one sample, and we are dealing with a mean or numeric variable, okay? It's easy. X bar plus or minus T star times S over the square root of n. And we will talk about what T star is. Okay? So again, you have these 3 bits, X bar, S, and N. And now you just have to find T star, okay? It's also worth noting that the standard error S over the square root of n is called the standard error, or SE. Okay. So when you were dealing with proportions and categorical variables, we also had the standard error, but it had a different formula. Okay? So the standard error is something that changes depending on what type of variable you have and whether you have 1 sample or 2 samples. Okay? So the standard error always changes. For 1 sample means your standard error is S over the square root of n. Okay, T star. How do we decide what T star is? We use the T table. Okay? And we're going to have 2 parts. We're going to have to look up, so to select T star, you need to know that your degrees of freedom is equal to n minus 1, and choose the confidence level. Based on the problem. So it's choose confidence level based on problem, and this says df equals n minus 1. Or maybe you're not talking to me. Okay. Alright, so let's try this out. So here is your problem. Okay. So, you go to a company. Of 845 employees. You take again, to select your T star, you're going to look in your table, and at the very top of the column, and we didn't go over this when we went over using the T table, because I think this part is easy enough that it didn't need explanation. At the very top of the column, it says confidence level. And so whatever confidence level is written in the problem, you look at that column, and you find your appropriate degrees of freedom to get the T star that you're going to use.
Yeah, it would be this one. So yeah, this is the example of 60. And then if you want to do percentage of that, that's when you divide the.
Okay, let's see, do you need another minute?
Yeah.
Okay, alright. Okay, well I put the answer up there, so if you're going through the problem and you're not getting that answer, then I'll show you how to get this answer.
Wait, is he doing it?
Okay, alright. Unprecedented, but let's see.
I'm sorry, I got like 4-1-7-3.
That's totally fine.
I wrote it wrong.
Yeah, totally fine.
I don't think the whole class had to know. Just quick question, you know what I mean?
Yeah.
So it's much better this way. Okay, another minute or are we good? Just do it, right? Just do it. That's what I will do. Okay. So, do we have X bar? So, if you're struggling with these problems, okay, it never hurts to just write down the information that's in the problem, okay? And you know, some of you feel like this is a waste of time.
No, it's not.
But it's not, you're right. Okay. So X bar is what? From the problem, X bar is 4.7.
Plus or minus.
S, no. We're going to figure out the letters that we have. Okay, S is
2.5.
2.5. Okay, remember when you're dealing with this type of problem, you got to figure out N, X bar, and S. Okay? So, and N is
63. Or 60, right?
63. Okay. Now we have to figure out our T star, okay? So for T star, we got to figure out our degrees of freedom, which is n minus 1. So degrees of freedom would be 62. Well, n is 63. 63 minus 1 is 62, right? Okay? But when we go to our table, we don't see 62, so we use 60. Okay? So in the table, use 60. Now, if for some reason you had a different T-table that had 62 degrees of freedom, of course you would use 62 degrees of freedom. But if your table doesn't have that, just use the next one. 60. Okay. And what is our confidence level? 90%. Okay. So our confidence level is 90%. So when we go to our table, we look at that column 90%, and we go to the row 60 degrees of freedom. And what is the T number that I have there?
1.671.
Yeah, T star is equal to 1.671. And I just want to take a brief moment to make sure that from the table we see T star should be 1.671. Good? Alright, and so now that we have all of this, we just plug it into here, okay? So x bar plus or minus T star times S over the square root of n becomes 4.7 plus or minus 1.671 times S 2.5 divided by the square root of 63, okay? And at this point, you can try out your calculator and make sure that if you do 4.7 plus or minus, so figure out this part. Don't try to do it all at once. Figure out this part, and you should get 0.526. Okay, 1.671 times 2.5 divided by the square root of 63. You should get 0.526.
What was the step you did to find out? Like, what did you do first? 1.671. You just wrote that whole thing out?
I just, if you're wondering what buttons I pushed on my calculator, I put 1.671, and I hit the times button, and I hit 2.5, and I hit the divide button, and I hit the square root button, and I hit 63, and I hit equals. I guess I could write scores around the 6 and the 3 also, because I had to hit those buttons individually as well. Okay, and so I got 0.526. Is this what we're getting? Now, if you have some minimally functional calculator, it might involve a few more steps, but
There's more steps to this?
no. Alright, if you have one of these calculators, you can do this and you'll be fine, okay? If you've got a weaker calculator, you might have to find the square root of 63 by itself first and do these things individually, okay? So do we get this? Alright, and so you do 4.7 plus 0.526, and you get 5.226. I will write this even though I feel and you do 4.7 minus 0.526. And that's it. It's easy. This part is easy, okay? That's it. Well, alright, then we have the interpretation, right? I would say I am 90% confident that,
How would you write that?
yeah, okay, so I will write that out for you.
Yeah.
Thank you.
You're welcome.
Wait,
Was that bad that I erased that?
no.
Okay, good. I would say I am 90% confident average number of years
I could have said, just where it's 30, where's the-
Remember, I got that, you know where you look at, that's right there, 1.174.
years people have worked at this company is between 4.174 and 5.226. Yes.
So that, like, if a question like this would come up on the quiz, and you would ask us to put it down, or write it, could I like get away with saying I'm 90% confident it's between 4.174 and 5.226, or should I
You
write?
know, I would prefer rather than
Okay.
saying
No, write it
it's
up. Yeah.
what you're talking about,
Okay.
okay? And if I were to ask the question, do we have evidence that the average number of years is not 5 years?
No.
Yeah.
That is the correct answer. The answer is no, and why is the answer no?
Because we do have evidence.
Not what I was looking for. Because 5 is within my interval.
Yeah.
Yes, okay? So it doesn't necessarily mean that it is 5, but we don't have evidence that it's not 5, okay? However, if I said, do we have evidence that it's not 7 years? You would say, yes, because 7 is not inside the interval. Okay. Was that okay? Do I need to write that on the board? We understand that part of the confidence interval, right? Okay. Good. So we got confidence intervals for one sample. Now we're going to do hypothesis tests for one sample. Let me just make sure we're on track with time. We are on track with time. Okay. You know what? Let's actually take a break. All right.